Hello everyone, welcome to hydropower. Today we'll be talking about the turbine draft tube or diffuser. Here we have present the turbine draft tube as you can see on the figure. The draft tube is a pipe of gradually increasing area which connects the outlet of the runner to the tail race. It is used for discharging water from the exit of the turbine to the tail race. In this figure, this point is the exit point of the turbine or the inlet of the draft tube, and this one is the outlet point of the draft tube, where the outlet point is inside the tail race water. This one is the tail race water level. Now from inlet of the draft tube to the exit of the draft tube, the height fall is said to be HS. Now let's talk about the key features of the draft tube. Energy recovery is one of the key features. Energy recovery helps in converting the kinetic energy of water leaving the turbine into potential energy, increasing the overall efficiency of turbine. The next one is reduce exit velocity. Draft tube helps in reducing the exit velocity of water, preventing air being drawn into the turbine and causing cavitation. Next one is improve turbine performance. Providing a controlled passage from the water, the draft tube contributes to the stable and efficient operation of the turbine. And the third key features of the draft tube is variety in design. It has a multiple design, shape, size of the draft tube. Draft tubes come in different designs such as straight draft tubes, elbow draft tubes, and trapped draft tube, each suitable for a specific turbine type and operating condition. This design of variety is also can be called as the types of the draft tube. Now let's talk about the types of draft tube. There are various types of the draft tube. Among them we have proposed some of the draft tube. Here we have present the conical draft tube. Here this point is the inlet of the draft tube and this one is the outlet point of the draft tube, and this the outlet point is inserted inside the tail water level. And the next one is elbow draft tube. In the elbow draft tube, the shape of the draft tube is similar to the elbow. The inlet point is smaller in dia and the outlet point is more in compared to the inlet diameter, where this HS represent the vertical height of draft tube above the tail race. After this, the next one is elbow draft tube with circular inlet and rectangular outlet. The shape of the elbow draft tube with circular inlet and outlet is like this. In the starting point is circular and the outlet point of the draft tube is in rectangular shape. And after this, we have another is moody spreading tube. In this, the draft tube seems to be like this, as shown in the figure, where the inlet point from the turbine is a single and it is divided into the two parts while going water out from the draft tube that is going to the tail race. Now let's talk about the draft tube theory. In this, let's consider a conical draft tube where HS equals vertical height of the draft tube above tail race and Y is the depth of draft tube from the tail race. From inlet to the tail race level is the height is considered as S, and below the tail race inside the water the height is considered as Y. Now on applying Bernoulli's equation on the section section 1 and section 2, that is the from inlet to the outlet. On applying Bernoulli's equation at section 1, the equation forms will be HS plus Y plus P1 by gamma plus V1 square by 2Z equals P2 by gamma plus V2 square by 2Z plus HF, where HF equals loss of energy between one and 2, or HS plus Y plus P1 by gamma plus P1 square by 2Z equals PA by gamma plus Y plus P2 square by 2G plus HF, where P2 by gamma equals PA by gamma plus Y, or P1 by gamma equals PA by gamma plus V2 square by 2G plus HF minus P1 square by 2G minus HS. On simplifying this equation by placing the value of P2 by gamma on this, we get the result is this. After this, the P1 by gamma equals PA by gamma minus HS minus P1 square by 2G minus P2 square by 2G minus HF. In this case, if P1 by gamma is less than atmospheric pressure, in such case there will be the limiting value for the setting of runner with respect to water due to cavitation. Now let's talk about the efficiency of draft tube. The efficiency of draft tube equals actual conversion of kinetic head into pressure head is divided by kinetic head at the inlet of draft tube. Equals V1 square by 2G minus V2 square by 2G times of HF is whole divided by V1 square by 2G, where V1 square by 2G minus V2 square by 2G minus HF equals AC. Actual conversion of kinetic head into pressure head. And V1 square by 2G minus V2 square by 2G is equal to theoretical TAC. Conversion of kinetic head into pressure head in the draft tube. If V2 equals 0 in this equation, then this equation will be B1 square by 2G only. This is called as the kinetic head at the inlet of the draft tube. So for today, we end up the session for this much. We'll come again with one new video. Till then, keep on watching our channel and don't forget to subscribe us. Thank you.